Jackie. And good morning, everybody. I hope you're healthy and well, and thank you so much for joining another exciting webinar. And today's topic is fascinating. It's the geologic history of the Niagara Escarpment, and we've got some wonderful guests that are absolutely qualified and experts in this field, so I'm really thrilled. Before I introduce our guests, I want to let you know that a few months ago, the Bruce Trail Conservancy and the APCO Education Foundation formed a partnership to create a ground-breaking trail experience using innovative technology, science, education, and research. And so a few months ago, Dr. Bill Pearson, who also happens to be a Bruce Trail member, is the chair of the foundation, and him and I met and signed a memorandum of understanding to bring geoscience and the environmental wonders of the Niagara Escarpment to the members of the Bruce Trail and also the general public. So today's webinar is a great example of the collaboration between the two groups, and we're really grateful for this opportunity. I do have the pleasure today of introducing our guests, and I've been lucky enough to meet them both in person, and myself, along with our terrestrial ecologist, Adam Brelowski, went to go visit them at their lab at McMaster University and absolutely have some fascinating research that they're going to be sharing with us today. So today we have with us Dr. Carolyn Eyles. Dr. Carolyn Eyles is a professor in the School of Geography and Earth Sciences and a member of the School of Interdisciplinary Science at McMaster University. Carolyn holds a Bachelor's of Science in Environmental Sciences from the University of East Anglia, a postgraduate certificate of education from the University of Newcastle upon Tyne, and a Master's of Science and PhD in Geology from the University of Toronto. She is a certified professional geoscientist in Ontario and is a 3M National Teaching Fellow. Her research involves analysis of glacial sediments and their origin, and she has conducted fieldwork in Ontario, Iceland, Alaska, Australia, Peru, and Brazil. Carolyn has recently become involved in the investigation of erosion processes affecting the Niagara Escarpment in the Hamilton region. So welcome, Dr. Eyles. And Rebecca Lee is a PhD candidate in the School of Geography and Earth Sciences, working with Dr. Carolyn Eyles at McMaster University, where Rebecca is completing her Bachelor's of Science and Master's of Science in Earth and Environmental Sciences. Rebecca's research has involved the use of remote sensing and drones in the investigation of glacial sediments and landforms in Iceland, having also worked in Southern Ontario and Peru. She is involved in investigation into the Niagara Escarpment erosion and applying remote sensing techniques to address the issue. So absolute warm welcome to you both, and I'll turn the presentation over to you. Thank you.
Thank you very much for that introduction, Michael. I hope you can all hear me. Thumbs up. Yeah, thank you. Okay, so we're going to talk a little bit about the geological history and some of the geological processes that are going on along the Niagara Escarpment. So really it is a story of ancient seas, glaciers, and waterfalls. So those are combined in our talk. So what we're going to do here is we're going to look, first of all, we're going to think about the formation of the escarpment rocks in those ancient tropical seas over 400 million years ago. We're then going to think about how the escarpment was actually created after deposition of these sediments and formation of the rocks. The escarpment's created largely by glacial and fluvial erosion. And we'll finish off by thinking about some of the processes that are affecting the escarpment today and some of the studies that we're conducting on these processes. So as an introduction, when we usually think about the geology of Ontario, I like to think of it in this kind of very simplified fashion. So at the bottom, at the very lowest level, if we drilled way deep beneath the surface, we get to the Canadian Shield, or the North American Craton, which is the oldest part of our continent. And this was formed by at least 1 billion years ago. So in Ontario, our Canadian Shield rocks are somewhere between 3 billion and 1 billion years old. Then lying on top of that is layer 2 here, shown in this diagram here with these blue colors, are the Paleozoic rocks that we're going to be talking about. These are sedimentary rocks, and they were largely laid down in ancient seaways that laid over our continent in Paleozoic time. So those are the rocks, those are the sediments that form the rocks that we now see in the Niagara Escarpment. And then following that, much later on, we had layer 3, which is a glacial layer. These are the glacial deposits that were laid down less than 3 million years ago. And then on the very surface, we have our built landscape. So we're going to be focusing on layer 2, the Paleozoic layer, because they're the main focus of the Niagara Escarpment. So if we look at, again, an image of Ontario, southern Ontario, and you can see on the right, it's a false color satellite image showing the contact that we can see between the Canadian Shield, those very old rocks that are over 1 billion years old, and the Paleozoic cover rocks, which lie to the south. So the Paleozoic rocks literally lap over the top. They form over the top of the Canadian Shield rocks. And here you can see around in here, you've got Rice Lake and Lake Scugog here and the Kawarthas. So it gives you some kind of perspective. So these Paleozoic sedimentary rocks, which are somewhere around about 600 to 350 million years old, cover much older Canadian Shield rocks, which are older than 1 billion years. And this is a map, a geological map of that same kind of area. Well, it's a little bit expanded, but we can see in the northern part, the shield rocks, the colored rocks shown here of the Canadian Shield. And then these buff and gray colored rocks here are the Paleozoic cover rocks, which overlie the Canadian Shield. So the shield hasn't disappeared, it's underneath these Paleozoic cover rocks. And if we took a cross section, if we sliced this area in two, across from approximately Kingston to London, and looked at it in the subsurface, we'd see something like this. So on the right is Kingston, and to the left is approximately London. And you can see the gray area at the bottom is actually the Canadian Shield rocks. Those are the North American Craton, Canadian Shield. And then on top, you can see these gray and blue, these pale gray and blue buff colored rocks here are the layers of the Paleozoic rocks that we're going to be talking about. And the red arrow there shows where the Niagara Escarpment lies. And then on top, we get a thin veneer of the glacial sediments. So that kind of puts us in perspective as to how these rocks lie in southern Ontario. So where do we see them? Well, we see these rocks beautifully exposed along the Niagara Escarpment, but also if we go down into the Niagara Gorge. And these rocks accumulated basically as sediments. They are all sedimentary rocks. We don't have any igneous rocks in amongst this succession. And they are the result of deposition in shallow tropical seas that covered much of North America during this time. So somewhere we're focusing on the time period about 450 to 420 million years ago. And if we look at what we call a stratigraphic column, which is shown on the right here, which is really a shorthand version of recording the different rock types that we see, we can see on the right, basically it's a stratigraphy of the Niagara Escarpment going from the Queenston near to the base up to the Ancaster at the top. And the colors there, the yellows and browns are mostly sandstones and yellow, and the browns are mostly shales, much finer grained deposits. And the blues are the limestones and dolostones. Okay, so we're going to talk about each of those kind of packages and the kinds of environments in which these different rock types formed. So let's go back in time and think about what the environment around Hamilton, I'm focusing mainly on Hamilton, what it looked like around, well, sometime before 440 million years ago. Very different paleogeography we had at this time. Hamilton, as you can see, was sitting on the shoreline, close to the shoreline of the Canadian Shield, and over to our east was an open ocean. It was called the Proto-Atlantic Ocean, the Iapetus Ocean. It was a big, wide ocean, and in that ocean was accumulating the remains of animals and organisms that lived in the ocean, and there was extensive carbonate reefs, and limestone was forming at this time. And so this is a little diagram showing this is our paleogeography at this time, very different to today. Continents were quite differently oriented and put together at this time. We were actually part of what we call the Laurentia. That's the ancient continent of North America. And this is a larger image to show that. So the red stars here are always where Hamilton is. So there's Laurentia, and Hamilton was lying on the edge of the continent at that time. And to the east was this broad seaway in which these limestones were accumulating. And these are the limestones of the Simcoe group, which are underlie most of the deposits that we can see exposed on the escarpment. However, there's one thing I want to point out here is look at Baltica on this diagram here. And Baltica is heading towards us, and it's going to collide with Laurentia. So Baltica is moving, and it's moving because of plate tectonic processes. We actually have collision going on. There's a subduction zone in between Laurentia and Baltica and Laurentia, because of plate tectonics, are being drawn together. So we get collision happening. And when Baltica collides with Laurentia, and there's Hamilton again in the red star, we get a mountain range produced, because when continents collide together, nothing happens, nothing goes down, nothing gets subducted into the mantle, but they actually, two continental plates collide together and create a mountain range, very similar to the Himalayas today. So this happened, and when Baltica collided with Laurentia, we got the Taconic Mountains forming. And these Taconic Mountains are very important as a source of sediment that now exists in the Niagara Escarpment. So when the mountains formed to the east, we no longer had an open seaway to the east, but in fact, another seaway developed to the west, and that overlaid the continental area of Laurentia. It was what we call an inland sea, and that extended to the west. So the kind of drainage in the paleogeography has shifted yet again. So this diagram at the bottom here shows what's happening. This is east is to the right and west is to the left. Baltica has collided from the east, and we have the Taconic Mountains have formed. And then towards the west, we have the sediments that are being eroded from the Taconic Mountains, being carried by rivers into the seaway, which lies to the west, and forming a large delta. And this is called the Queensland Delta. And it's a large body of sediment which extends out into the seaway to the west. And these are the sediments that now form many of the rocks that we see exposed in the Niagara Escarpment. So moving on, this is a diagram at the top right here showing that kind of, it's a schematic diagram showing that delta. And it's actually termed the Queensland Clastic Wedge, because it is actually a wedge-shaped body of sediment. And it extends from the Taconic Mountains on the right-hand side there in towards that inland sea towards the, to the west. And we see these deposits being recorded in the Niagara Escarpment by a series of deposits, mainly at the base of the escarpment, series of rocks we can see exposed in the escarpment. Everything going from the Queensland Shale, the Whirlpool Sandstone, the Grimsby, the Cabot Head, all the way up to the Thorold Sandstone. So if we go down to Bronte Creek in southern Ontario, we can see great exposures of the Queensland Shale. It's this red shale. And that was formed as at the kind of the far end of the Queensland Delta. We don't have a lot of sandstone here in the Queensland Shale, but this is the shale that's carried out on the delta edge. And we can also see the shale, and there's the star where the Queensland Shale is. We can see the shale well exposed elsewhere around southern Ontario. Usually exposed as red shales, this really red color with thin gray bands. Very well exposed at the Devil's Punch Bowl in Hamilton. The Caledon Badlands expose the Queensland Shale. And even further north, we can see the Queensland Shale exposed at Big Bay. So this is it's a major kind of shallow, muddy deltaic deposit, the Queensland Shale. And all of this sediment has come from the Taconic Mountains, carried by rivers into that inland sea. Things change. And on top of the Queensland Shale, what probably happened was water levels decreased, so the sea levels dropped, and we get a series of fluvial deposits, river deposits. So the Whirlpool Sandstone which is named after a good exposure that we can see of the Whirlpool Sandstone in the Whirlpool Gorge at Niagara. This is a kind of a solid sandstone horizon unit that was formed by rivers. Higher energy, so it's coarser grained, larger particles here. And the sandstones form in channels and they form crossbeds. And we can see here on this upper right, these are crossbeds here. And these are formed by dunes, sand dunes, which migrate along the base of a river. So along the river floor, you get these sand dunes migrating and they get preserved as crossbeds in the sandstone. On this figure here, on this photograph, we can see the Queensland below, and we can see a sharp contact here with the Whirlpool Sandstone on the top. So this is because the sandstones are deposited by fairly high energy flows, and we often have a very sharp contact when they come. They enter on top of a shale or any other kind of unit beneath. So we can see the sandstone well exposed in Niagara Gorge. We can also see it at the Devil's Punch Bowl in Hamilton. And this photograph on the lower right, again, shows the Queensland Shales at the bottom and the Whirlpool Sandstone sitting on top here with those big crossbeds in it. Okay, so it's an interesting unit. So we get more shales and sandstones accumulating in this Queensland clastic wedge, but we have one very interesting unit in a little bit further up the stratigraphy in the Thorold Formation. And the Thorold Formation contains a lot of sandstone. It also contains some shales, but we can see here some really unusual features. And these are what we call sandstone pillows. And if you look at this photograph here, we can see flat-lying units of red and gray sandstones and shales down here. There's relatively flat-lying deposits on top. But these units here in the middle are all kind of these bulbous units, look all deformed. And the same with this unit down here. It's one of those big pillows. And what's happened here is that the sandstones that were accumulating on the seafloor at the time have been disturbed by seismic shock. So what's happened is that probably an earthquake has affected the area, and it shocked the sediment, and the water has escaped from the sediment. And as it does this, it deforms the sediment as it escapes to the sea floor. So this horizon here is what we call a seismite, which is a record of an ancient earthquake. So here we have in the Thorold Formation the record of an ancient earthquake that happened probably about 430 million years ago. So it's pretty cool information there that we can get from some of these sediments. And we can see this, it's regionally extensive, this earthquake horizon. We can see it well exposed at the Jolly Cut, at the Devil's Punch Bowl in Hamilton, and you can see it elsewhere too. So there we have a delta developing in this ocean and in this inland sea. It's prone to some earthquakes, it's prone to some shallowing and periodic fluvial deposition. So let's think about how things are changing between the Niagara area and Hamilton and up towards the Bruce Peninsula. So I'm focusing mainly here in the talk on what we can see in the Hamilton area and the Niagara area, but there's very similar things happening in the Bruce Peninsula, although remember the Queensland Delta wedge. The wedge is going from, it's extending from the southeast towards the northwest, and hence the sediment is going to get finer and finer grained as we move from the southeast to the northwest. So when we look at the stratigraphy in the Niagara Gorge here and Hamilton, we can see plenty of sandstone and mudstone. When we get up to the Bruce Peninsula, which is shown here on the left, it's mostly limestones, and limestones develop in seaways that are clear and clean water. We don't need a lot of muddy sediment for limestones to develop. So here we can see that by the time we get up to the area that is now preserved in the Bruce Peninsula, there was very little sediment in the water, and it had all fallen out or been deposited near towards Hamilton and Niagara. So it's further away from the sediment source up into the Bruce Peninsula, and we get these limestone units forming in clear, clean water. So things like the Dyer Bay, the Lion's Head, the Colport Bay, and the Wyerton formations all developed in this way. And then the Guelph Formation is part really of the Lockport group, which I will talk about in a moment, but it's part of that upper limestone, dolostone rich unit. Okay, so once the Queensland clastic wedge had formed, things change. If you notice on the logs here, the stratigraphy from the Niagara Gorge and Hamilton, towards the top, we've got much more limestone and carbonate rocks developing here, which tells us that, again, we're moving towards a much cleaner, clearer water environment. And what happened was around about 430 million years ago, the Taconic Mountains stopped uplifting. So basically collision had stopped, the mountains ceased uplifting, and so we got much less erosion of the mountains, and sediment supply was reduced, greatly reduced. So we had no longer any sand or mud coming into the area. We had clear, clean waters, and these are ideal conditions for carbonate reefs to develop. Lots of organisms, filter feeders, and they developed these carbonate reefs. Hamilton would have been a gorgeous place to live in at this time. Tropical reefs, absolutely fabulous. So the depositional environments around about 430 million years ago. We have these tropical seas, probably less than 10 meters deep, nice and warm. We were in a latitude that was somewhere between the equator and 30 degrees south, so it was nice and warm. We had local patch reefs. We had carbonate platforms developing. It was very, very nice, like the Caribbean today. So a very pleasant environment. And these deposits are recorded in the stratigraphy of the Niagara Escarpment by the uppermost units. Those are the carbonate units. So they're recorded by these limestones and dolostones that we see in the Lockport and the Irondequoit towards the top of the stratigraphy. So there's a picture showing the Lockport. We in the Hamilton area, Niagara area, the Lockport is certainly the uppermost unit that we see. The Irondequoit is also a carbonate layer. It's a dolostone layer, and it's a very distinctive layer. When we look at any of the cliff exposures, it forms a solid band of about a meter and a half thick, cutting across the cliff face. Between these limestone or these carbonate layers, we do get some mudstones. So there is a little bit mud comes in, and we get the Rochester Shale, which is slightly different, has a different texture and different kind of resistance to erosion, particularly, than the Lockport above and the Irondequoit below. So here we have an environment dominated by these carbonate formation, but we do get occasional shales coming in as well. So I thought I'd add a little thing here about what's the difference between limestone and dolostone, because I've said both. So limestone basically is the original rock that forms when organisms, their shells fall to the base of the sea. They're made of calcium carbonate, the shells. They decompose and they disintegrate and they form as a limestone. It's mostly calcium carbonate. Over time, that limestone can get changed. And what happens is some of the calcium ions get replaced by magnesium ions, and we produce a calcium magnesium carbonate. And this happens after the limestone is a rock. It's a solid rock at this time. But fluids that pass through the rock can allow that change to occur, that replacement to occur. And when dolostone forms, what happens is you get a volume reduction. And because it's a solid rock, the volume reduction ends up producing a series of cavities in the rock. And these are called vugs. And these are what you can see in most of the dolostones that you see at the top of the Niagara Escarpment, in the Hamilton area, in the Lockport Formation. You can see these beautiful kind of cavities peppered around the rocks, different sizes, but those are vugs produced by this dolomitization process. So the change from limestone to dolostone. But both limestone and dolostone are carbonate rocks. They both indicate deposition in warm tropical waters, nice, clear, clean waters. So a little bit about what was living in these Paleozoic seas, these nice tropical oceans. Well, we had a variety of life forms here. We have brachiopods, some various types of brachiopods, lots of corals developing. We have what we call sea scorpions or eurypterids that were kind of pretty scary little creatures moving around. Our good old trilobites crawling around on the seafloor and swimming in the ocean there. And cephalopods. And cephalopods are like giant squid-like creatures. And they were carnivorous, and I guess they were pretty nasty as well. So they were big predators. And here we have a kind of diorama showing what it would be like on the seafloor around the Hamilton area about 430 million years ago or so. And there's a good old cephalopod gobbling up a trilobite. One of my favorite fossils is the crinoid, and we can see lots of crinoid fossils in the escarpment rocks. Crinoids are called sea lilies, but they're not actually lilies, they're animals. They were attached to the sea floor, and they had a kind of a head with a stem that had waving tentacles, and these tentacles gathered food particles in from the water. They were filter feeders. And they had a stem that consisted of calcium carbonate discs that are called ossicles. And when the animal died, those ossicles fell to the seafloor, and they are what we see preserved in many, many of the escarpment rocks, particularly the Lockport and also the Irondequoit. Any of those carbonate-rich rocks we can see as those little discs. We used to call them St. Cuthbert's beads when I used to find them on the sea shore up near, this is in Britain, because they looked like beads that have been kind of broken off a necklace or something. But these are those little round things there that you can see here. Those are our good old crinoid ossicles. So when you see those, you know you've got crinoids around. Okay, so the Lockport Formation, we call it the cap rock of the Niagara Escarpment in the Hamilton area. It's the very uppermost unit. It has two members. It has an upper member called the Ancaster member, named after Ancaster, where it is very well exposed. It consists of quite thin beds. They're very thin and they're highly fractured. They're all broken up. In fact, the Ancaster most often looks like brickwork. It looks as if somebody's just had a pile of bricks there. And it contains, the Ancaster contains these white nodules of chert, which are a silica deposit. And then underneath the Ancaster is the Gasport member. These are both part of the Lockport Formation, but there's two different types. They're slightly different environmental conditions. These are thicker beds. They're both dolostone. Thicker beds, fewer fractures, less chert. And this is equivalent to the Amabel that it has a different name in different areas, but it's equivalent to the Amabel. So you may see that further north in the Bruce Peninsula. So what happened after the Lockport was formed? So that's our cap rock. And on the escarpment in Hamilton, we don't see any other Paleozoic sediments preserved above the cap rock. What happened about 420 million years ago was that things got hotter. We had serious climate warming at that time, became much warmer, much more arid. We were closer to the equator. And basically what happened was the seaways that were inland, those inland seaways dried up. And they produced these salt flats, tidal flats, what we call sabkas. And this happened repeatedly and repeatedly. And basically ended up producing a whole lot of salt. So the salt deposits that we find around the Windsor area, which are shown in the pink area here, so around from Goderich down through Sarnia into Windsor, these salt deposits here are really the remnants of that ancient inland sea. So as it dried up, it shrunk, and those salt deposits are what we have left. So next time you see some road salt going on, you know where it comes from. Okay, so we have nothing on top of the Lockport Formation here in Hamilton. So between about 400 million years and about 300 million years, we don't have any record. There's no record of any sedimentation here in the eastern part of North America. And so we assume that the eastern part of North America was exposed. And a lot of the pre-existing rocks that may have been deposited on top of the Lockport and so forth have been removed by erosion. And prior to about 3 million years ago, we know that the continent, northern North America, was covered by, or was scoured by, a series of rivers. And one of these rivers was the ancient Bell River, which extended and actually flowed through Hudson Bay to the north. But then around about 3 million years ago, we got dramatic climate cooling, and we started to develop a series of glaciers, or large ice sheets, that covered the continent repeatedly over the last 3 million years or so. So, for example, the Laurentide ice sheet, which was our most recent ice cover here in northern North America, that there's an example of it, but these ice sheets developed repeatedly over the last 3 million years. And obviously, had an enormous impact on the continental surface and scoured a lot of the ancient Paleozoic deposits away. And you can see just by this figure down on the lower right here, the dramatic change in the drainage patterns that have been caused as a result of the repeated glaciation of the northern part of our continent. And this is basically what leads into thinking about how the escarpment itself has formed. And I'm going to pass on to, I'm going to mention this about our Paleozoic rocks. Going back to this diagram that I showed you earlier, the Paleozoic rocks that we see, the grays and beige and buff colored rocks here, they are not absolutely flatline, but they have a slight tilt. So they dip gently to the southwest. So that means that the layers that we see the edges of each of those layers, and we see the older rocks in the east, and the younger rocks are preserved to the west. And the resistant rocks that we have that form the cap rock of the Niagara Escarpment are those that have been actually preserved because they are able to resist the forces of erosion more easily than the weaker shales. So this is again to remind you how we're sitting with the Niagara Escarpment. There's the tilt, there's the dip on those rocks, on the Paleozoic rocks, and you can see how the Niagara Escarpment is created by that Lockport dolostone. So now I'm going to pass over to Rebecca, who's going to tell you some more about the formation of the actual escarpment.
So now that all of the rocks have been kind of laid down, we're going to talk about the formation. And a lot of this comes from the erosion of those multiple glaciations that Carolyn was just talking about. And we're eroding the dipping Paleozoic rocks backwards to form that steep face. So it actually started up where the Canadian Shield was and stripped it back further and further from the northeast to the southwest where we see it today. And so it's kind of just gradually moved backwards. So the glaciers kind of plucked the rocks and rivers, all of this combining to move the escarpment from where it was to where we see it now. So although the rocks of the escarpment are quite old, from past 400 million years, the escarpment itself is a young landform that's actually still developing. So we're talking about the erosion of the escarpment. It's because it's geomorphologically active. It's actually moving backwards consistently, as it's been doing for a long time. One of the places we can see that is at Niagara Falls. So we know that in the last 12,500 years, so basically since the last ice sheet retreated backwards, it's moved about 10 kilometers to the southwest. So it's had about 10 kilometers of erosion. And so that's partially because after the glaciation, lots of meltwater, lots of rivers, high energy, and so you're getting a lot of erosion occurring. We do have some historical evidence from 1678 showing how far it's gone back. The Niagara Falls is not the only place that this happens. Lots of similar processes occurring across the escarpment. For example, we have the waterfalls here in Hamilton, the city of waterfalls, like Tiffany Falls, where you're seeing basically the same process occurring, just on obviously a much smaller scale than Niagara Falls. Another impact of the erosion is what we call outliers. So these are just areas of really particularly resistant rock that haven't been eroded in the same way as the rest of the escarpment around it. So for an example, we have monocliffs, which is north of Orangeville. So looking at that little map in the top right, you can see that the red part is the higher part. And so the kind of the edge there, that's the edge of the escarpment. And just off of that edge to the, yes, there, perfect. Those outliers are also created of the Niagara Escarpment, but they've been separated from the escarpment edge itself. There's other areas that have similar things. There's the Milton outlier, there's flower pots, which are a similar idea, but a little bit smaller scale, where resistant rocks have held a form together. So at monocliffs, for example, the escarpment has actually been cut by a large meltwater channel called Violet Hill Meltwater Channel about 13,000 years ago. And again, that kind of dates back to the deglaciation when all the glaciers were going away and all that meltwater was coming. You can see in the little map, it's showing the rivers actually going around the outside of the outlier and kind of carving that shape that we see today. So the outliers of the escarpment rock are really occurring because that resistant cap of the Amabel is holding it together, as well as there's probably some sort of weaknesses around it, making the meltwater and the rivers want to go kind of around it rather than trying to erode through it. And that's really why you're getting outliers kind of sitting just off the escarpment face. Okay. So what type of erosion processes are affecting the escarpment? We know that water has a lot to do with it. So we have the movement of water over the escarpment rocks. So we've mentioned it before, but Niagara Escarpment has that resistant, what we call a cap rock, which is a Lockport dolostone. And that just means it doesn't erode very easily because it's quite hard. And so it takes a long time for water to make its way through it. But underlining all of these resistant cap rocks is a much weaker rock, often the Rochester Shale. And shales erode much more rapidly due to the nature of their composition and the small grain size. So when you're at like the escarpment edge and you see all that debris at the base, it's usually mostly made of clay, which comes from these shales. So as it is eroded more quickly behind it, it ends up that the cap rock is basically sticking out from the escarpment edge. And at some point, the weight of the resistant cap rock exceeds what it can take and it just breaks off. So it kind of leaps backwards. And we know that this process called undercutting is a significant cause of retreat of Niagara Falls, as well as the escarpment as a whole, because we're seeing this kind of alternating, really resistant and soft rocks. We also have movement that is going through the escarpment rocks. So it's kind of easy to see, though of course you can't look into the rocks themselves, but during the summer, when you see vegetation growth on the rock face and you see the different plants coming out of them, like there, it's a pretty good sign that there is water coming out of that area. So you know that that's one of the paths that water is escaping through the ice, through the face of the rock. And in winter, it's almost easier. If you drive by, you'll see icicles seemingly just coming out of the rocks. And those are areas that you have water seeps. So again, water is coming out of the rock there and forming these nice icicles. This is really important for erosion because we have to think about freeze-thaw weathering in this area. So the water gets into the cracks of a rock, and when the temperature dips below zero, the water then freezes, of course, and expands and starts cracking the rock further. So it keeps breaking the rock in little bits. It will then thaw and then freeze again. And over time, you're gonna break apart rocks or you're gonna loosen them from the rock face. So this can actually be a pretty critical method of erosion, especially in colder climates or kind of our types of climates in temperate areas. So we know kind of what processes are probably occurring, but we don't know a lot of things. We have a lot of questions. How quickly is escarpment eroding? What processes and rates, how they're being affected by different things. So what are the factors affecting them? How those processes and rates vary along the escarpment. So is everything that's happening in Niagara Falls the same that's happening in Hamilton, the same that's happening in the Bruce Peninsula, or are there lots of differences? And then if there's differences, which areas would then be most susceptible to erosion? Which areas do we have to think about preserving, the trails and the infrastructure around them? And then always talking about kind of looking to the future, it's will climate change affect erosion processes and rates? We know that water and temperature is a big kind of consideration. So how is that going to change as the climate continues to change? So what are we actually looking at? These are examples from the Devil's Punch Bowl, which we're using as like a natural example of the escarpment and its erosion. So we're looking at the effect of lithology on erosion processes and rates. We've already talked about how some rocks are more or less resistant to erosion, but kind of going deeper into that, the differences and what we expect to see. We're also looking, of course, at the role of surface and groundwater. So again, how is that going to impact the rate of erosion? And if that differs from location to location, what does that really mean for the escarpment itself? We're also looking a lot at the fractures. So it's all those cracks in the rock face because they definitely affect the processes and rates and also how big pieces fall off. The Ancaster has small blocks, smaller pieces compared to others. We have this example from Do It Road because it just really highlights the impact of fractures and erosion. You can see here that in 2014, there's that big piece of rock. And then when you look into 2018, that rock has now fallen off the escarpment. That's a colleague of ours. And you can see not only did that rock fall, but a large area of the escarpment face has actually fallen as well. So we're looking at these types of erosive events and seeing what's happening. And we're also going to look at vegetation. There's potential impacts of vegetation, whether it's stabilizing, whether the roots are actually increasing the erosion, the mosses and stuff, how these all kind of work together to affect the rate of erosion that's occurring along the escarpment face. And all of these different things we're looking at work together in order to create a full picture of the erosion that we're seeing. So we hope to get a lot of these studies. We're looking to have a better understanding of the geological history of the escarpment, specifically within Hamilton and how that's evolved. A better understanding of the processes affecting the escarpment today. So we want to know what's happening, how fast is it happening, to partially make sure everyone is safe and think about infrastructure and homes that lie close to the escarpment. Once we do that, we'd like to identify the areas of high risk. So which areas are most likely to be have these rockfalls? Hamilton's had a lot of rockfalls in the last decade or two. And so it's kind of why are those happening where they are and where are other areas we should be thinking about? And then finally, identifying some mitigation measures. Of course, there's mitigation measures in place already, but just to know if those measures are the best possible way to protect the escarpment and the people who use the trails and the roads near it.
And I think most importantly, we're trying to create information and provide information to the public about the Niagara Escarpment, about its fascinating geological history, and also about the processes that are going on along the escarpment today. So we're doing this, as Michael said, we have a collaboration now between the Bruce Trail Conservancy and APCO Educational Foundation. And we are creating a series of virtual field trips that we're going to focus on the Niagara Escarpment so that people can appreciate the immense beauty and scientific value of the escarpment from their own desktops or living rooms. We already have a series of virtual field trips that are posted on the APCO Educational Foundation website, which is www.geoscienceinfo.com. And those are two examples of some of the maps that we have with some of the sites of our field trips are already identified here. We do have a virtual field trip that already exists for the Niagara Falls area. So we're really wanting to extend these virtual field trips to cover the Niagara Escarpment along its length, really. We're focusing right now on the Hamilton area, and then we intend to move northwards up through the Bruce Peninsula. We'd also like to create some geotrails, which would actually focus on parts of the Bruce Trail and identify specific points of geologic interest along these the trail. So these are all works in progress, and we're working on those hopefully as soon as we can once we're allowed back in the field again. One of the things is, though, we'd like to appeal for your help as members of the Bruce Trail Conservancy. We really need some information from you. We'd like to gather information from people who are using the trails or observing the Niagara Escarpment. The more of us that can observe the escarpment and feed in information to a repository, the better. So if you have any information or questions about interesting or unusual geological features along the trail, we would like to hear from you. We would really appreciate any photographs you have of features such as collapse features or anything that looks unstable. If you could tell us the location as well, or maybe if you have any older photographs of parts along the trail that seem to have changed dramatically over time, we'd like to see that too. So if you could send any of that information to Megan Kroll, through the Citizen Science program, that would be absolutely wonderful, because again, the more information we can garner about things that are happening along the escarpment, the more we can do with this information. So I'd like to thank you very much for listening. I hope this has been an interesting exploration of what we consider the fascinating geological history of the Niagara Escarpment. It's an amazing landform. We're very privileged to have it in our backyards. And I open it up to any questions you may have. Thank you.
Well, thank you very much. That was absolutely exciting, and I learned a lot myself. We do have some questions, and so I'm happy to put you on the spot and throw those over to you now.
Sure.
The first one's pretty easy, though. I think you're going to like this one. It just says, "Wow and wow, so interesting." So, congratulations. Great. I think that is an opinion of everybody that's on this webinar. The next question comes from Susan Spire. It says, does human use have an impact on the escarpment? As an example, a large number of hikers or mountain bikers. So could you please speak to that?
That's a very interesting one, and it's a one that we are actually delving into as well. And yes, human use will have an impact, certainly in along trails and wherever there's really exposed rock that may be loosened, or if the trails are damaged in any way, it may accelerate water erosion. Particularly, we can get gullies developing in some of these trails. So we have to be very vigilant about keeping the trails well maintained so we don't get gullying. On a larger scale, we've also been looking at the impact of historical mining, quarrying on the escarpment, which does oversteepen parts of the escarpment, and also even urbanization on top of the escarpment, particularly in the Hamilton area. We have a lot of urban development there. There's a lot of swimming pools that are very close to the edge of the escarpment. They load the rocks on the escarpment, and they also leak. And that contributes more water to penetrate through the rocks of the escarpment, which can enhance erosion rates as well. And that's something that we're, again, studying and trying to study. It's part of our kind of water flow through the escarpment study. Yeah, so they're very good questions though. So I'd like more information about human use of the trails though as well.
Okay, fantastic. Thank you very much. There's a comment here that says, fantastic presentation. What caused the slope in the Michigan Basin?
Ooh, that's a good one. There's a variety of, it's kind of some sagging going on. There's what we call a couple of arches, which have been basically pushed up that separate the Appalachian Basin from the Michigan Basin. And the arch, the Algonquin Arch, actually divides the two basins. So it's basically old structures that are causing the formation of those distinctive basins, much older. But yes, it's basically the kind of tectonic underpinning of our continent that's causing the warping that's creating those basins.
Okay, thank you. The next question is, what is a karst, and can we find it along the entire length of the escarpment?
Okay, I have one slide here because somebody asked me something about karst in the Beaver Valley, and I wasn't sure how to incorporate it here. But basically, karst is a product of the dissolution of the carbonate bedrock by rainwater, groundwater, which is slightly acidic. And it's that dissolution process. So we do see it in all of these carbonate rocks, the dolostones and the limestones. It is quite extensive in this area along the Niagara Escarpment and the Bruce. There's some interesting publications that I can suggest to you. There is certainly a karst map of Southern Ontario that I've mentioned there. And the karst really has developed in multiple phases because during glaciation, the drainage systems on these rocks are very different to when we don't have glaciation. So we have basically an inherited karst system from when it was when the area was glaciated, and now it's deglaciated. So it's quite an interesting development of the karst. But we do see it extensively along the edges of the Niagara Escarpment and also in areas where the carbonate rocks are exposed on surface.
Okay, thank you. That's great. I've got a comment here that just said this presentation makes me feel young, so that's nice. There's a question here that said, would you be interested in knowing where lime kilns are located?
Oh yeah, that would be very good too. Yes, yes, I would be interested in that. So yes, please.
Okay. There's a question here that says, awesome presentation, thank you. Is it an option to have the trails we use reviewed to see if they're built to cause more erosion and if we should reroute the current trail? And so I'll take a super quick shot at that, just saying that we do look at building sustainable trails, and that's definitely on our radar, but I'd be happy for you to try and speak to that.
No, I would love to work with you. And one of the things that we're planning to do is to identify particular areas on some of the trails that may be at risk from some collapse of some of the escarpment walls. So we would love to, and we plan to, work in conjunction with the Bruce Trail Conservancy to look at these features, and we can garner some information from them, but we can also maybe together work out the best way to protect these areas.
Yeah, that sounds great, and I can happily agree to that for sure. So, and then last question here are, when things relax, will there ever be an in-person field trip? And I don't think we've defined that yet, but I know that's something I'd be happy to collaborate with you on for sure.
Absolutely, we love doing field trips, and I'm hoping that once we get through COVID, that yes, we'll be able to run a whole series of field trips along really interesting areas. So yes, I'd love to do that. Okay,
great. And then Carolyn, Rebecca, I just went through the questions that came through during the presentation. Did you have any others that were emailed to you before, or we've addressed them all?
I think the ones that we got emailed to us before, I've tried to incorporate into the talk. So, but if anybody has any other questions afterwards, please don't hesitate to contact us, because we're very interested.
Okay, great. Well, sincere thanks to you both for an amazing presentation. Like I said, I think we've learned a lot, and it's interesting when we're out hiking, we have a whole new dimension to think about when we're out there exploring. So thanks for making it accessible to us. I know I'm excited to go look for sea lilies or ossicles the next time I go hiking. And just thanks to both of you for your expertise and your work and your partnership.
Thank you. And thank you very much for the invitation to come and do this. It's always our pleasure. Thank you.
Thank you.
Okay, great. Have a great day, everybody. And thanks for joining us today.